Imagine a universe where nothing ever changes. No movement, no temperature variations, no atomic transitions, nothing. In such a universe, would time exist? Not really. Time is the measurement of change, the ordering of events, the difference between what was and what is. Every clock you've ever seen is simply a device that counts change. The swing of a pendulum, the vibration of atoms, the rotation of Earth. This leads us directly to our next concept. If time is tied to change, then the laws that govern change must also govern time. And that brings us to thermodynamics. In everyday life, time feels like it flows in one direction, forward. Eggs break but never unbreak. Smoke disperses but never undisperses. Memories form about the past, not the future. This one-way flow is called the arrow of time, and it comes from a single principle, entropy. Entropy measures disorder. And according to the second law of thermodynamics, entropy in a closed system always increases. The universe began in a state of extremely low entropy, and ever since it's been moving toward higher entropy, which gives time a direction. The arrow of time exists not because the universe demands it, but because entropy creates it. This brings us naturally to the physical nature of time itself. For most of history, scientists believed time was absolute. Isaac Newton described it as a single cosmic clock that ticks uniformly everywhere, independent of matter or motion. In this view, everyone experiences the same time. Events happen in the same order for all observers. Time never speeds up or slows down. This makes sense intuitively, but the universe is not intuitive. And as soon as we looked at nature through the lens of high speed, high gravity, and high precision, Newton's time began to break down. That breakdown opens the door directly to Einstein. Einstein's theory of relativity transformed our understanding of time. He showed that time is not fixed. It's relative, flexible, and intertwined with space. Together, space and time form a single entity, space-time, and the structure of space-time changes based on speed and gravity. Let's look at how. The faster you move through space, the slower you move through time. This is called time dilation. If you fly in an extremely fast spaceship, your clock will run slower compared to someone on Earth. It's not a glitch, it's how the universe works. This isn't hypothetical. GPS satellites must correct for time dilation daily. If they didn't, navigation on Earth would be off by kilometers within minutes. So motion changes time. But there's another factor that slows time down even more. Gravity. Gravity also affects the flow of time. The stronger the gravitational field, the slower time passes. Close to a black hole, time slows dramatically. A few hours near the event horizon can equal years far away. This gravitational effect is measurable even on Earth. Time at sea level runs slightly slower than at the top of a mountain because Earth's gravity is weaker higher up. So now we have a deeper truth. Time is not a universal drumbeat. It stretches, bends, and warps depending on the conditions of space-time. This naturally leads to a bigger question. If time can warp, does it even exist independently? Relativity treats time like a dimension similar to space. You can move forward in time effortlessly, but unlike space, you can't turn around or step sideways. In this view, time is part of the geometry of the universe. Events don't happen so much as they exist in space-time. Like pages in a book, your consciousness simply reads them sequentially. This brings us to a profound idea. In the laws of physics, the past, present, and future all exist simultaneously. There is no universal now. Different observers, moving at different speeds or in different gravitational fields, disagree on what now even means. Once you understand this, a new question appears naturally. If physics doesn't define a universal present, why do we feel one? Your brain creates a sensation of now by stitching together sensory information into a continuous moment. This moment lasts about a few hundred milliseconds. It's not physics, it's perception. Your sense of time is shaped by memory, expectations, dopamine levels, attention, biological clocks, so when time feels slow or feels fast, that's your brain adjusting its internal model, not time itself changing. But if time is partly a human construct, where does physics place the boundary between past and future? This question leads directly back to entropy. Here's something strange. Almost all fundamental laws of physics work perfectly fine if you reverse time. Electromagnetism, gravity, quantum mechanics, they look the same running backward. So why doesn't reality run backward? Because entropy gives us a direction. It doesn't break the laws. It sets the initial conditions. The universe started in a highly ordered state, and everything since has been unfolding toward disorder. This one asymmetric condition is what creates the forward flow of time. But if we zoom down to quantum mechanics, time becomes even more puzzling. At the quantum level, particles don't behave according to classical time. They exist in probabilities, superpositions, and entangled states. Some quantum equations don't even include time as a separate variable. This has led some scientists to suggest that time may not be a fundamental part of reality. Instead, it might be an emergent property, something that arises from deeper, more fundamental processes. One idea is that time emerges from quantum entanglement as information moves from order to disorder. Another suggests that time arises from the universe's expansion. That time is just a measurement of increasing spacetime. Quantum gravity theories like loop quantum gravity and the Wheeler-DeWitt equation treat time differently or remove it entirely. But all of this leads to one final question. If time is not fundamental, then what determines the universe's future? This takes us to cosmology. Dark energy is accelerating the expansion of space. As the universe expands, galaxies drift farther apart. Over trillions of years, stars will burn out, matter will decay, and the universe will approach a cold, empty state. This is called the heat death or big freeze. Entropy will reach its maximum possible value. With no gradients, no energy differences, and no change in time, as we experience it, will effectively stop. Time began with low entropy. Time ends when entropy is maximized. The beginning and end of time are tied to the universe's structure itself. This brings us full circle to the ultimate question: what then is time? Time is not just the ticking of clocks or the movement of planets, it's a measurement of change, a direction created by entropy, a dimension woven into space-time, a variable that bends under motion and gravity, a perception created by the brain, and possibly an emergent property of deeper physics. We move through time not because it pushes us, but because the universe evolves. From order to disorder, from simplicity to complexity, from the Big Bang to the distant future. Time is a story of change written into the fabric of reality. And we are temporary travelers inside that story, moving along one chapter at a steady pace from what was into what will be.